So hello everyone, this is Diksha this side, and I'm not going to waste any of your time in introducing myself or about my channel. So I'm straight away going to start. Many students struggling in slope and deflection wala part in strength of material. So we used to have a double integration method to find out the slope and deflection of various kinds of beams, like simply supported beam, cantilever beams, propped cantilever beams, and so on. But what we can see here is that the double integration method is so cumbersome, so lengthy, so boring method. It will take a lot of time. But yes, I'm not saying that this is not useful method, or we should not use this method. We can, or you want to find out the slope or deflection in a very quick manner, then you should aware about the Macaulay's method, which we usually use to find out the slope and deflection of any part inside the beam in case of unsymmetrical loading, right? So let us first understand uh, how exactly double integration method looks like, what is the complexity of this method. Okay, so let's have a look to it. Okay, so let's learn the complexity of method of integration. As you can see, this is a simply supported beam having a point load W, or we can say concentrated load W, acting at distance A from left support, and we already know how to find the reactions at the support. Like, if you know how to find the reaction, that is very good, absolutely great. But if you don't know how to find the reactions, you can comment over below. I'll definitely make a video how to find reactions altogether. Okay, so without wasting any time, we just straight away go and see what is the bending moment equation for this beam at any distance x from left support, right? So we have assumed a distance x from the left support. So we can write bending moment equation. So as you can see, we either have to see left side of the section where we have cutted our beam. We either have to see towards the left section or towards the right section. So what I'm going to do is I'll see towards the left support. So if you see towards the left support, you can see very clearly that there is only one reaction force which is acting over there. So what will be the bending moment equation? It will simply WB A plus B multiplied by distance x. And if I talk about whether it is hogging or it is sagging, so we can clearly see that it is sagging. Why sagging? Because for the left side, if you are writing bending moment equation for left side, you can see the reaction support tends to rotate the beam in clockwise manner, right? And if clockwise manner is present in the left support, we can say it is sagging, right? So we have already written our bending moment equation. We can write it as M, but now let us write. We already know that. Hope you guys are aware of. Just a second. Hope you guys are aware of these equations, like y double dash ei is equals to m, right? That is what I have written over there. Y double dash ei is equal to, as you can see, this is whole my bending moment. This is bending moment. So if you integrate this once, you will get y dash. What you will get? Y dash. We can see over there WB A plus B EI we have kept same, and if you integrate x, it will become x squared by 2, and this is a constant A which will arise, right? Now the next step is what exactly is this? This is representing the slope. This is representing slope at any distance x from the left support. Now we will integrate it once again to find the deflection. Now if we integrate once again, we will get y is equal to WB A plus B EI will be kept as a constant. We can take it out, and x square will become now x cube and 3 नीचे आ जाएगा. So basically 2 into 3 is 6, and if we integrate a, it will become ax plus b. B is another constant that we have introduced while doing integration, right? Now what we have to do, we can't find a deflection or slope unless and until we have we get to know about what exactly the values of a and b. So we have to find the values of a and b in order to get the values of deflection and slope. So to get the values of deflection and slope, we are going to use boundary condition. What exactly the boundary condition that we can apply here? As you can see there, like due to this load, the beam tries to go downside, right? But as there are supports, so there will be at end P and at end R, there will be zero deflections. So the first boundary condition will become, at x is equals to 0, we have deflection, y is equals to 0. So put these values. As you can see there, I have used a boundary condition that at x is equal to 0, y is equals to 0. So if I use these use these values in this equation, I'll get b as 0. So I have already find out the value of b. Now it's turn to find out the constant a. Now how we are going to find out the constant a? For that, we are going to use another boundary condition, that is at x is equals to a plus b, also also deflection becomes 0. As you can see over there, I have already said that at left support and at right support, and at right support, the deflection is going to be 0. So we have already used the first boundary condition. Now it's the time to use another boundary condition, that is at x is equals to a plus b, y is equals to 0. Okay. Can we use this boundary condition for this equation, for this bending moment equation? No, we can't. Yes, actually we can't use this boundary condition. Why this is so? Because we find out the bending moment equation for PQ section only. We have taken our section in PQ region only, but the boundary condition we are trying to use is also include QR section as well. So we are not allowed to use another boundary condition, that is at x is equals to a plus b, y is equal to 0. If you want to use this boundary condition as well, then you need to have bending moment equation in QR region as well. Okay, and as you can see, I have written over there at x is equal to a plus b, y is equal to 0. This can't be used as this doesn't lie in the region for which we have written bending moment equation. You can clearly see over there, we have written our bending moment equation for PQ region only and not for the QR region. Hope this makes sense, right? So what we are going to do now, we are going to write the bending moment equation for QR region as well, right? So if we cut a section in QR region and taking it at a distance x from left support, that is P, you can see there will be now two loads acting. There will be two loads are acting, that is the one load is reaction at the support, and another load is W. The reaction at support is acting at a distance x from the region. We have cut down our section. You can see there, I can make a separate diagram that is like this. This is like WB divided by A plus B, and this is another W. This is another slope reaction at the support. I am not going to write it. I have cut it down the section in the region QR, you can see PQR at distance x, and you already see that this W is acting at distance A from left support. So what we can now we can write the bending moment equation for QR region as well. You can see there that WB divided by A plus B acting at distance x from the region that we have selected. So it is giving sagging, it is giving us sagging bending moment. ये हमें sagging दे रहा है. And what about this W? This W gives us hogging bending moment, and it is acting at a distance x minus A. So that's why I have written minus WX minus A. Why minus? Minus because it is giving us hogging bending moment, right? So now we are ready to move ahead. So we have written the bending moment equation. Now again we are going to use this equation as well. This equation again. Now we are going to use this equation once again. Like as you can see, y double dash EI, y double dash, I have already written y double dash M by EI. You can see over there. I have already used the values of M divided by EI. Now what I'm going to do, I'm going to integrate this whole equation. I'm going to integrate this whole equation. Now after integrating, what I'll get, WB A plus B will be kept as a constant. Then x का integration we will do, so we will get x square by 2. Now minus W will kept as it is, and you already know that the integration of x is x square by 2, and minus minus becomes plus WA, and integration of WA is I think you people are knowing that integration of WA dx will become nothing but WAX, right? So plus another constant we have introduced, this is another constant, that is, let's say this is A2. Why A2? Because I have already named A1 above, right? Divided by EI. Now what this gives us, what? Slope. Yeah, this is giving us slope. Now we are going to integrate the whole equation once again in order to get the deflection at any distance x from the left support. So as you can see, the method is already becoming so cumbersome, and yeah, definitely it doesn't take out our interest, because we already know like how to integrate and all the things, but it's just increasing our number of constants. As you can see, we have already get 2 constant in above equations. Now it's time to gain 2 more constant values, 2 more unknown values. So as you can see that the method of integration is becoming so cumbersome, so lengthy method, that there are number of constants are going to increase, but the number of boundary condition is only 2. We have only 2 boundary condition and 4 unknown. Now I hope this makes sense, that this method becoming so complex to solve, right? So this was basically the demonstration of how complex the method of integration can be. Okay, so what is the substitute of this method? The substitute of this method is found by Macaulay. Macaulay has found a very great method, very good method, that we can solve this kind of beam, in within a matter of 2 to 3 minutes, not more than that, right? So okay guys, so now I'm going to discuss what are the rules. There are some important rules that we need to take care while using Macaulay's method. The rule number 1 is to do things for the last segment. What does it mean? What does it signify? It means that if you have I'm going to draw there, this is a simply supported beam I'm drawing, and you are having, let's say you are having 2-point loads. It is not visible, wait, yeah, now it's visible. So it is having like 2 loads, W1, W2, and let's mark these regions A, B, C and D. So guys, now you are having 3 regions in this beam, that is region number 1 A, B, B, C and C, D region. So as per Macaulay's method, it says that do things for the last segment. That means you should always write the bending moment equation for the last segment of the beam, that is CD segment. Don't write bending moment equation for AB section, BC section. Always write for the last section, that is the last segment of the beam. I hope it makes sense, right? So basically, let's take the total distance x from the left support of the beam, and up till the section you have cut it down, and these distances will be already known to you, that W1 is acting at distance A, and let's say that W2 is acting at distance B from left support. These distances will already be known to you. So let us move ahead. Don't worry, I'll make separate video for the practice of question itself. So right now we are just learning what are the rules that we need to take care while using Macaulay's method. So now the rule number 2 is, when term becoming negative, drop that term. What does it mean? क्या मतलब इसका? So I want to show you something. Like, let us write the bending moment equation for CD segment. Like CD segment mein we are going to write the bending moment equation. So as you already know that there will be some reaction at the support, at the left support. So you can clearly see that R1 is acting at a distance x. So we are going to write it like R1 into x. And what kind of bending moment it is giving us? Definitely there is no doubt it is giving us sagging bending moment, sagging, because we are looking at the left support. And left support is trying to move the beam in the clockwise sense. Now what about W1? First of all we will discuss sagging or hogging. So it is giving us no doubt hogging. So use minus sign W1. Now it is acting at what distance? It is acting at x minus a, matlab x minus a. This at this distance. So this is clearly x minus a, right? Now what about W2? W2 clearly again hogging. So minus W x minus b. Now this is the complete bending moment equation. That we have written for the given beam. Now the second rule is saying that when term becoming negative, drop that term. What does it mean? It simply means that, let's say I want to use some boundary condition. Let's take at x is equals to a. It will simply become a, and this will become a minus a. It will become 0. Now what about this a minus b? Now this term will becoming less than 0. That means negative. Why this is so? Because you can clearly see there a is less than the b. A is a distance which is lesser than the b, right? So we could not take any term which is becoming negative. So if you took x is equals to a, this term will become negative. So simply ignore this term. This you would not take into the consideration at all. Okay, now let's move ahead. So I have written there that you can see over there terms like x minus a, then x minus b. So we are not going to integrate the you already know this equation, right? Y double dash ei is equals to bending moment, right? So what we are going to do, we are going to write it like that, y double dash divided by m by ei. Now we are going to integrate these equation. If you integrate once, you will get slope. If you integrate this twice, you will get what? You will get deflection. So while integration, we don't integrate x minus a like x square by 2 minus ax, or x minus b like x square by 2 minus bx. No, not at all. If you do so, then there is no purpose of Macaulay's method. So please, this is very much important point to note down here, that the integration of x minus a will not be doing simply like that, x square by 2 minus ax. This is not to be done, right? So what we are going to do, we are taking x minus a as a whole x. So what is the integration of x minus a dx? Consider it as a whole x. So the integration of this term will become x minus a squared by 2. Hope you get this point. Great. Let's move ahead and let's see what exactly the rule number 4. Okay, the rule number 4. Now we are going to see what exactly the rule number 4. The rule number 4 is, if we are going to have any concentrated movement acting in the beam, right? अगर आपके बीम में कोई भी concentrated movement act करेगा, now what you how you are going to write the bending moment equation? It is very simple, very easy, very easy. Let's just take care that this is A, this is B, this is C, and let's say this is D, this is E. I have already said that you have to follow the rule number 1, that is, do things for the last segment. That is, you can't write bending moment equation for AB section, neither for the BC nor for CD. Then you have to write the bending moment equation for DE section only. That's why I have cutted a section over there in D region only, at a distance x from the left support. Now you can write the bending moment equation very easily, that R1 into x giving us second bending moment. Similarly, W1 is acting at x minus a. इसको reduce कर दिया, then this distance will become x minus a. W1 into x minus a giving us hogging bending moment. Similarly, W2 acting at x minus b distance giving us hogging bending moment. Now what about this MO? MO is basically a concentrated moment acting inside the beam, right? So what we are going to do, we are simply going to write MO into x minus c to the power 0. Why this is so? Because this is the specialty of Macaulay's method, right? This is the specialty. I have already told you that we are not treating x minus a like x square by 2 minus a x. We are not doing the integration like this. Instead of that, we are doing like this. So this is another specialty of Macaulay's method, that we are going to multiply our moment as x minus c. Why x minus c? Because our moment is acting at this distance, this much distance, which is x minus c raised to power 0. Why raised to power 0? Because yeah, this is already a moment, and you know that moment is Newton meter itself. So if you make this power 1, this will include one more meter. It will become Newton meter square. But if you can see there, this is a bending moment, which is again Newton meter. So here it is Newton meter, but here it is Newton meter square. This you have disturbed the uniformity of the dimensions, so we can't do like that. So we are not writing x minus c to the power 1. No, we are writing it x minus c raised to power 0. Hope you are getting everything right. If you are having any doubt regarding the whole thing up till now I have discussed, just feel free to comment below, right? Okay, so perfect. So I hope we are moving so smoothly and you are getting everything right. So the rule number 5 and last rule, so just smile, because we are going to end this topic now. The rule number 5 is basically, if you are having any UDL acting, in your beam, so just simply extend your UDL up to the section you have cut it down, right? The section up till the section you have cut it down, extend your UDL, and then counterbalance it as well by applying equal and opposite UDL. Now write bending moment equation. So for the UDL, it doesn't mean like for UDL only we are doing like this. We will also going to do for UDL, for UVL, and so on, right? So we are going to just extend our UDL up till the section we have cut it down, and then we counterbalance it too, right? So I just wanted to show you how to write bending moment equation for the UDL in case of Macaulay's method, right? So this is not any reaction support, okay? So for the UDL our bending moment equation will become like that. This is W, this is whole W. It is acting at a distance. This whole is x, and it is acting at a distance x minus 3, and of course y negative, because it is giving us hogging bending moment, hogging. Now below we have one more UDL, this and you can see this is again W, and it is acting at a distance. The whole distance is x, and this much distance is 5, this much distance is 5, so it is acting at x minus 5 distance. Okay, it is acting at x minus 5, and definitely it is giving us sagging bending moment, right? So now we are done with Macaulay's method. Now I'll bring some tricky questions, some great questions to practice Macaulay's method. Hope that you enjoyed this concept. If you find any kind of query, or you did not get any point, just feel free to ask anything in the comment section. I'll be definitely revert back each and every query of yours, right? So this is so far. Thank you. We will meet next time with some beautiful questions.